Okay, let's finish up section 2.1 here. This should go faster than the first page, I hope. Talk about different kinds of relations. Let's talk about discrete versus continuous relations. A discrete relation is a set of individual elements, and the graph would be disconnected. So basically a bunch of points is a good way to visualize it. Continuous relation contains an infinite number of elements, okay? Graph as a line or a smooth curve. That's how we represent an infinite number of elements or an infinite number of points, is with a line or a smooth curve, okay? I don't have a lot to say about that, I don't think. So you've got a picture there of a discrete and continuous. Let's move on here and let's talk about this graph. So right here we have the graph of y equals 1/2 x minus 3. We want to determine the domain and range to determine if it's 1 to 1, whether it's discrete or continuous. Well, this is just a line, and we've already talked many times about how to graph this relation. And we haven't talked about it in terms of a function, but that's fine. So let's plot the y-intercept there at -3. It's got a slope of 1/2. So we're going to go up 1 over 2 and up 1 over 2. And there's our line. Okay. So the set of x, y points, or elements, but the set of x, y points that make this equation true is represented by a continuous line. There's an infinite number of points, and the line represents them. Let's figure out what the domain is. The domain is all of the x values, all of the inputs that have outputs, all right? And so if you were to list out all of the x points, there'd be a lot of them. There'd be an infinite number of them. Not only that, but it would cover everything, right? This line is going to keep going up forever, to the right forever, and it's going to keep going to the left forever. So the domain here is all real numbers, okay? So we can denote that with this fancy uppercase R, or you can write out all real numbers, all right? The range is going to be the same. The range would be all the y values that the graph covers. So if you were to list out all the y values, you would cover all of them, right? Because this graph is going to go forever down, and it's going to go up forever, all right? So yeah, we'd say that this has a range of all real numbers. And again, we can use the fancy R. I'm going to use that because it's a short way. You can write out all real numbers if you want to. Determine if it's 1 to 1. Well, let's get rid of this yellow here. If it's 1 to 1, it will pass the horizontal line test, which means there's no point where a horizontal line will cross, no place where a horizontal line will cross more than one point, and there isn't. So this function is 1 to 1. So let's write that down. Yes, 1 to 1. And then what else do we want to know here? Domain, range, 1 to 1, whether it's discrete or continuous. This is continuous for sure. So yes, it is continuous. All right, let's move on. Independent and dependent variables. The independent variables are the variable values that make up the domain. These are the values that don't depend on anything. Quite often in real world problems, it's time. Time is the independent variable because time doesn't depend on anything. Lots of times the thing you're measuring depends on time. That's not always the case, but think of independent as it stands alone, doesn't depend on anything else. The dependent variable obviously then must depend on something else, must depend on x, must depend on the independent variable. Okay, these are the variable with values that make up the range. Okay, so independent variable, often x, dependent, often y. Okay, so you want to lock that into your brain somewhere. Let's talk about function notation real quick. In fact, let's move this up a little bit before we do. Let's talk about function notation. So let's let y equals 2x be an equation here, obviously. Now we know that we can graph this line, and we know that it's a function. It will pass the vertical line test. I don't think I said that on the last example. That was definitely a function though. We know this will pass the vertical line test, so we know it's a function, so we should be able to write it in function notation. What does that mean? Well, before I show you that, let's talk briefly about some of the points that we know would be on the line. So if we plug in 0 for x, we know that we would get out 1 for y. Do a little bit of computation, you'll get 1. And we know that if we put in 1 for x, then we will get 2 plus 1, which is 3, right? And we can keep doing this for lots of points on the line. So as I'm saying this, I'm kind of setting the stage for function notation. I'm saying if we put in 0, out will come 1. If I put in 1, out will come 3. So I can write this equation in function notation like this. I would write f of x is equal to 2x plus 1. I'm just exchanging the y for f of x. Watch why this is useful. if I want to put in 0 using this notation, this is what it means. I go find f of 0. 0 is the input, and that just means that wherever I see an x in the function, I'm going to put 0. So that'll give me 1. All right? So that's how you write it in function notation, and that's how you can generate points. Inputs go in for x, outputs is what happens after you compute it. Okay? So given this function here in the next one, number 4, f of x equals 2x squared minus 8, I want to find f of 6. Well, then I just write 6 in the parentheses. I go 2 times 6 squared. I'm going to put 6 in parentheses. You should always put the number that you're putting into the function in parentheses, especially if it's negative. Okay, otherwise you'll make a mistake when you compute it. Minus 8. All right, you can use your calculator for this if you want. I've got it written in front of me. This ends up being 72 minus 8, and so you end up with 64 for this one. Okay, now that's a straightforward example. We can make it a little bit worse than that though. So we can come over here and we can start with this function, f of x equals 2x squared minus 8. Let's find f of 2a. Now, what I love about function notation, it doesn't matter if you're plugging in a number, a letter, or a number and letters. It doesn't matter. The property still holds. Okay, so I can take f of x and go f of 2a. That means everywhere I see an x in this function, I'm going to put 2a, and I'm going to use parentheses. Okay, so here we go. This is going to be 2 times, and then again in parentheses here, I'm going to put 2a, that's what I'm plugging in, squared minus 8. There's two places students make mistakes here. One is inputting it without parentheses, then you're likely to make a mistake in the simplifying, and then the second place is in the simplification. So you really want to be careful and pay attention to order of operations. So what I end up with here is 2 times, I'm going to do what's in the parentheses first. Okay, so it's going to be 2, everything in the parentheses, by the way, gets squared. 2 squared is 4. A squared is just a squared minus 8. And then we're going to simplify a little bit further. 2 times 4 is 8. So I get 8a squared minus 8. And there's nothing to do with that, okay? This type of problem is just trying to help you understand how functions work. It's not that you're going to get down to a specific number. It's just, can you plug this in and simplify correctly to show that you know how function notation works. One quick note on function notation, it does not mean f times x. It means f of x. It means f of whatever your input is, and then you're going to compute something to get what the output is, what the y value is. And that's it for section 2.1.